Good morning. So maybe some people still coming in, but we'll start picking up from what we left yesterday. Do you have questions from yesterday? Okay. So from now we'll talk about the permutation of the equations, permutation of the matrix. We usually call this reordering, to see whether we can reduce, finding a good ordering so that the LU factors could have as small as possible the amount of field. And this was the example I showed you, is the typical, the most extreme case, the arrow matrix. And if you flip around, then you see that when you do GE, then you won't get any field, okay? So then there are, of course, we have to deal with all the general matrices, could be any sparsity pattern. So then people have developed a number of algorithms to work with a general graph. So here I give you one example. It's slightly more realistic compared to the previous one. So this one, you can see that the left picture here is you can think about it's coming from a 5-point stencil, the standard PDE problem with a regular discretization, regular grid discretization. And then suppose you follow this order, just to do this natural ordering, then all the red dots here will be the field elements, the field entries. So that's generated. And on the right side of the figure I showed you is using an algorithm called a minimum degree ordering. So it's the same number of non-zeros to begin with. It's the same as the one on the left. But to begin with, the positions after this permutation, all these non-zero, the blue one, the positions will be different from here. So it looks not very nice. And then you do elimination, you still get a field. So in very rare cases, you don't get field. You always get field. But then you count the number of fields, the non-zero of this factor compared to it here. You see the advantage with this minimum degree ordering. You reduce the field from 233 to 207. And this is only a very small matrix, 25 by 25. So if you blow up the problem, this difference between these two orderings is actually asymptotically more. The amount of field is much more. It's related to the mesh size and the matrix dimension. So it's very useful to get a good ordering. And there are two big classes of ordering algorithms, which I will show you. But then there's some others. So the first class I'd like to show you is minimum degree. And we can see this, it's relatively easy to explain the algorithm. So we look at GE of first step. And now we basically, the algorithm and also implementation is not working on the matrix, it's working on the graph. But it's easier to look at it in the beginning both ways. So, and it's this particular algorithm is working on the symmetric elimination. So I start with a symmetric matrix. It doesn't matter what the values here. So the first equation variable is connected to ij and kl, to 4 of them, right? And then you look at the graph of just this portion of the matrix. So node vertex 1 is connected to ijkl, 4 vertices, right? And I don't know, I don't care right now about the connection between ijkl. And then after first step of elimination, you can see that all the portion of the submatrix, the short complement, you will get field. It's after elimination of this guy, you will get all field. So it becomes fully connected from the graph point of view. So what this says is that it's a very simple elimination rule. Is once you eliminate, look at the graph, once you pick up a vertex to eliminate, right? Once you eliminate, remove this vertex, all the neighbors will be fully connected. And in a CS term, this is called a clique. And then you can imagine that you giving a bigger graph of the original matrix A, and every step the game is just to try to pick up the vertex, and then it remove that vertex, make the neighbors become a clique, and then next step pick up another vertex to eliminate it. Continue doing this until everything is all the vertices are gone. So this is the greedy approach, meaning that you try to do the best locally. So every time you look at the local picture and then to try to find the best you can do local to make some optimization to minimize the field you generated at this particular step. So then the question is, which vertex do you think I should pick at each step?
Maybe the most far from the diagonal.
The far from the diagonal? That's not quite right. So I want to remember my goal is to minimize the number of these red guys generated. Minimize the clique I generated each time. So you are given a graph of A, then there are n vertices, right? The first step is which vertex you want to choose.
Minimum degree.
That's right. So that's why they call minimum degree. So suppose you have, why are you laughing? Suppose you have two vertices. One has degree just means how many neighbors, the number of neighbors. One has a 2, one has a 10, and then if you remove this 2, you generate a clique of size 2. But you remove 10, you generate a clique of size 10, right? 9. Yeah. But another thing is I want to mention is so this is a local approach to greedy, and also it's not exact. And it's that's why all these it's called a heuristic. Why is it not exact? Because I'm saying right now, pessimistically, I say I will generate these 1, 2, 3, 4, 2, 3, 4, 5, so many edges, the red. So all these are red. But to begin with, maybe some of these entries are already non-zero. So this count of these 16 elements is the upper bound. It's not the exact how many you have generated. To compute the exact is more expensive. So for minimum degree algorithm, people don't do the exact. They just look at this clique, look at the upper bound, try to minimize the upper bound. There's another similar kind of algorithm. It's called a minimum deficiency or minimum field, which really looks at, for example, if originally you already have 3 non-zeros, then you look at the 16, subtract 3 to count more exact. But that's more expensive to implement, and it takes the benefit is not tremendous big. So the game is simple. You just eliminate the vertex with the smallest degree, and then you have to update. So once this vertex is gone, you have a graph of size n-1. Then you need to update these degrees of the neighbors, because the neighbors. So all these neighbors will be affected. Their degrees will change. So you have to do some bookkeeping to keep track of those. And so that's the rule is simple, but the thing is implementation-wise, if you just follow this, it's very slow. Also, it requires more memory. Why does it require more memory if you just do this? Require more memory than original matrix A. It's more than A. Because you have to keep track of the red edges, the field, right? So every time you change the graph, you add some edges, then you need to keep bookkeeping to do that. So then people have developed a more clever scheme to do this. And this is something called using the quotient graph as a more compact representation. So what does this mean is look at each of the clique, right? You don't need to represent all the edges. And you know this is a clique. Then you just say, I have a clique of size 5. You just need to record the 5 vertices. And then as long as you mark these 5 vertices as a clique, implicitly you know you have all the edges connected among them. Okay, so that's what this quotient graph does. And then, what these clique, they also use each of these connected components, this eliminated subgraph, they use a single supervertex as long as all these within this big supervertex, each vertex, they are indistinguishable from each other, so you can use this as a single unit. And the outcome of using this quotient graph model is that when you run this minimum degree algorithm, the storage required to run through this algorithm to find the label, the ordering 1 to n, the vertex numbering, is actually can be implemented bounded by the size of A. So that's very nice, right? Because remember yesterday I mentioned that the field ratio could be 20 or 50 for the 3D problem. So if you are implementing this naively in a straightforward way, so your graph, the size of your graph could be 50 times larger than the original graph. So that's very important from an implementation point of view. And then also in implementation, there are a lot of papers about different variants, a lot of very detailed issues about, all these heuristics, you always have, every little thing you need to make decision, and there are different decision making, then you can have different variants of the algorithm. And a few years ago, the model I talked about was for symmetric matrix. A few years ago, several of us, we did extend this quotient graph model to the non-symmetric bipartite graph, which I'll mention briefly later. Okay, so that's the first class of algorithm. The second class the first class is a local greedy approach, and there's no guarantee about a global quality of the ordering. The second class is called a nested dissection, and it's generalized to graph partitioning. So it becomes a very useful tool in scientific computing to partition the big problem into smaller pieces. And the paradigm here using is a divide and conquer. So it's a global top-down approach. So here I start with a simple case. That's you do for example, solving the Poisson equation on the regular 2-dimensional grid. And usually the picture I showed you, if you number like this picture, if you number your grid point, like row by row, row by row, or column by column, like in that order, then you'll get somewhat like this more or less a banded matrix, okay? So that's, people usually say, naturally, I want to order this in this way, by row or by column. But here, the nested dissection is looking at the numbering differently. So what we do here is, for example, I take out these set of vertices. I number them last. So they are, so altogether in here, I have 49 grid points. And then I number this set from 43 to 49. And the 2 halves we can do, maybe this half first, that half second, okay? So then if we look at our, recall our field path theorem, and then you can imagine now you can think about where is the field generated. For example, you want to see whether between any vertex, for example, of 18 and 39, or 18 and 15, is there any field generated? So how can we think about it? So the way to think about it is our theorem says that after some vertices x1 to xi are eliminated, then the set of nodes adjacent to y, so all these, the field edge yx, for example, this x has to be in this reachable set from y, going through all the vertices which are already eliminated. So these vertices, they have numbering which is smaller than x and y. So they are already eliminated. So that means looking at these 17 and 38, do you think there will be, in the field graph, in the LU factor, do you think there will be an edge between 17 and 38? Between 17 and 38. Will this 17, 38, will that be connected in the LU factor? Will be a field or no? Just a guess, yes or no?
No.
No. Okay. Why? Just guess, yeah. Well, you got a good guess. I want to see something behind your brain.
The grouped nodes aren't all less than the min between x and y, right?
Right. So what happens here, 38, you cannot find any path, so 38 is our y vertex, for example. You cannot find any path which is coming from 17, but going through all the vertex set which is smaller than 38, right? You have to cross over this boundary, this cut. Is that right? So that's why, in the beginning I was mentioning this reachability, reachable set, reachability property. It's a very powerful tool for you to think about, just at not at a lower level, each detail, but at a higher level to think about where is your field going to be. And at least here, you know that these two halves, they will not be connected. They will not generate any field between any vertex on the left side, D1, to any vertex on the D2. And then on the picture here is that D1 will not, this part will not have any connection here. They may be connected to the S part, but not connected between them. Okay. And then I have a second question is, what do you think after elimination, this piece, all these 1, 2, 3, 4, 5, 7 by 7 matrix, which corresponding to here, and what's the structure, sparsity structure look like? So this structure, to begin with, it's like your 5-point stencil, right? Each one is connected only to 4 neighbors. But my question is, after GE, after elimination, just still look at this little 7 by 7 matrix. What's the structure, sparsity structure look like? Still apply this reachability theory.
If we have divided that into 2 sets, we just have local fields in D1 and D2. So in the sense that we don't have fields anywhere else, just in these 2 blocks.
Yeah, field will be here. And now my question is looking at this part. So these are 7 equations, 7 variables in the end, right? So corresponding to the matrix here. And where the field, they will generate a field. Some field will be generated at this corner. And then my question is, how many field will be generated? Can you? It's not irregular. It's regular. It's some very regular pattern. Can you think about what pattern it is? It's very interesting. I'll spend some time on this. I think you have an answer again. Still think about the reachability. So for example, think about 49 and 43 between them. Will this 43, 49 be filled? Still look at this property, this theorem. It says each vertex it's going to generate a non-zero yx as long as this x is in a reachable set going through all the eliminated variables. Okay, so my question is 43, 49 is filled. So to begin with, they are not connected, right? The connection is only between here, pairwise here. But it's these 49, 43, they are far apart, they are not connected. And afterwards, what about?
We're eliminating just the nodes in S?
Right. So by the time you get to here, all the D1 part is done. D2 part is they are all eliminated. So you get to the last piece. Okay. Okay. It's still not clear, huh? So the answer is they will be connected because you can find a path between 49 and 43 going through the previous vertices, right? So any pair of the vertices within this, we call this a separator, by the way. Any pair of vertices here, 45, 48, you can find a path which goes through the previously eliminated variables. So what does that mean? What's the sparsity pattern of this guy? It's entirely full. Okay, so that's a very important property is you do this nested dissection give you the different ordering, and then but the matrix, submatrix corresponding to the separator is actually those little blocks. The block here is entirely full. Okay. Okay, so we spent some time on this, but that's okay. So then that's one level bisection. We find a one level partition the separator, split the graph into two. And then you order the separator last, order the two pieces first. And after that, it's, of course, that's only give you the first level bisection. So the algorithm works like recursively applying this scheme. So you got to the first level D1 part, you continue to find the separator. And then for that part, continue to find the separator. And then you can see that with this nested dissection, the graph after reordering, the sparsity pattern of the graph will look like this. Okay, and then as I mentioned, all the separator piece will be dense. So that means this piece is dense. And then the piece corresponding to this brown one, it's here, after elimination will be dense. This piece will be dense. The blue one here, the blue one after this will be dense, after this will be dense. And then this nested dissection will give you the ordering like this, and then it can be, the dependency elimination order can be precisely described by this elimination tree, also called a separator tree in this case. So you first eliminate 7 to 9 in this picture. I mean, there's some stuff going on at the bottom. But just look at the separator. This is 7 to 9, eliminated first, and then 16 to 18 second, and then 19 to 21 here. And on the other side is 28 to 30 is one separator, and so on. And by the time you get to the top step. So this elimination tree gives you the dependency of the whole GE. How do you follow this? Okay, so then what's the complexity? And the nice property of this algorithm is that for a certain regular graph, you can actually show proof that this ordering gives you the best possible, they give you the optimal order. Whereas for the minimum degree algorithm, you cannot prove anything like this, even for this regular graph. So that was actually invented, this ND was invented 40 years ago. And in fact, a few weeks, last week, 2 weeks ago, we just had a meeting in Waterloo to celebrate the invention of nested dissection ordering for Alan George at the University of Waterloo. So what he has proved is that apply ND by a sequence of plus separator. So we use a plus separator. It's a little bit relaxed because for line separator, then you have one piece which becomes not a square anymore, becomes a rectangular. So therefore it's harder to do the arithmetic, to do the counting. So we use a plus separator. Top level is a plus separator, then the second level is this purple plus separator. Okay, do this ordering. Then using this reachable set argument, all the separators are dense, and then the field, you estimate the field by adding up all the non-zeros in the separator. So that gives you a kind of the first order approximation. So for example, if your grid start with is a k by k grid, right? So then the first level separator, the dense matrix will be k squared. And then the second level, you have half of the grid size. And then it's k divided by 2 squared. So it's a geometrically Then at the second level, you have 4 of those, so multiply by 4. The third level, you have 16 of those, and the size of this, the dense matrix is k over 4 square. Okay, so it's just adding all these together. In the end, you can calculate the number of non-zeros. In the factors, it's order of k squared log k, right? And then k squared is the number of equations, the dimension of the matrix. K squared is n, so it's n o n log n. Okay, so then you see that there's already a factor blow up here, even for this 2D problem. So the original number of non-zeros in the matrix A is 5n, right? You have 5 diagonals for 5-point stencil. But now it becomes, there's a factor of a log there in the field. So it's a nonlinear. There's a question or? No, okay. So in fact, Alan George has done more precise calculation of this, and then he found out the constant before this prefactor is about 9 something, 8 something. And then similarly, you can do the operation count, floating point operation, and also mainly based on the dense, small dense matrices at each separator. Then the operation count is given its order of n 3 over 2. So it's also not linear. So compare with for this kind of problem, if a conjugate gradient could work, then it will be faster conjugate gradient. So the this factorization will be slower. It's not linear. Okay. So that's just to summarize the complexity here. And you can do the similar analysis for 3D. So what's the separator of 3D cube? It's a plane, right? So you do the similar analysis for 3D plane, and the grid size is k by k, so the number of equations is square root of n. And in this case, it's k cube, the number of grid points. So number of equation will be n. So sorry, this n is the size of the mesh. So the number of equations here will be n, and the size of the mesh will be cubic root of n. So for 2D, we did the analysis like this, and for 3D, it's even worse. The number of field in the LU factor is n to the 4/3, so it's even more than this. And the number of floating point operations, which is related to time, is n squared. Okay, so 3D problem, just to give you just one sentence to say, 3D problem for direct solver is even more costly. And that's in the beginning, I mentioned that for 2D problem, we see something like field ratio 10 times, but for 3D, you can see 50 or 100. So that's pretty typical. Okay, so then the rest is, once you understand that, the rest is relatively simple. We need to generalize this to any graph. So instead of just restricted ourselves to the mesh. So then the technique here is you start with a big graph corresponding to your matrix, and then try to find the separator. And this is very technical, a lot of research on this. And then reorder the matrix, put this separator last, and then 2 pieces A, B first. So the question is, what's the optimization criteria you want to find the separator? Whether you want separator S to be large or you want separator S to be small. You know, if you are giving a graph, there are a lot of separators, right? A lot of way to split to find the vertices to split the graph. And my question is, you want to find the vertex set S, which is as small as possible or as large as possible? Small as possible. So if S is small, this 0 block will be big. So then this 0 block is preserved, right? So then you essentially maximize the 0 block, minimize the field. So that's the critical thing, is to find the separator which is as small as possible. And there are a lot of different heuristics. And currently the software available Oh, there's a typo here. It's a meters or par meters without this A. So it's available. You can download another software. Very good software is Scotch or Parallel. It's a PT Scotch. So the sequential and parallel, sequential, parallel. So those are the very mature software, and people use those a lot in scientific computing. And then the different papers, they talk about different ways of finding the separator, finding small separator, and recursively multi-level scheme, etc. So those are more the research front. And then you can take a look at after this multi-level Nancy dissection ordering. So your matrix to begin with is like this banded structure, right? And then after Nancy dissection, I got the first level separator here, split into two pieces, and look at each piece. I have the second level separator, again split into two pieces, third level separator. So that's I did the symmetric permutation of A using this Nancy dissection ordering. And then you can see that the non-zero, we do the GE using this pattern. Then the non-zero will be filled only within the part of the matrix corresponding to the separator. So the different components, A, B, the two parts, the little zero block, they are preserved. So you still get a lot of fill. You know, it's a lot of this red stuff fill, but it's constrained, restricted within this pattern, within this separator pattern. And looks like a very good pattern, right? Okay, so that's this. And another one useful ordering, it's different from this tool, is called Cartier-Mackey, and also reverse Cartier-Mackey, so it's a SIAM, RCM. And this is available in MATLAB. Also, minimum degree ordering is available in MATLAB, but MATLAB right now doesn't have a Nancy dissection ordering. So what does this algorithm do? The goal here is actually to reduce the bandwidth. Remember, we're talking about the matrix, the bandwidth. And then the algorithm works is for any graph, you pick a vertex to begin with, then just do the breadth first search of this graph. Meaning that every time I explore the neighbors of this vertex, and then I build the level set. So after I build this neighbor, at any level, the priority is given to a vertex with a smaller number of neighbors. Okay, so the next vertex, so for example, you start with this, you build the first level set is 2, 3, 4. And among 2, 3, 4, which vertex do you want to start expanding? Is either 2 or 4. They have the degree of 2. So this guy is gone. They have a degree of 2. 3 has more connection, more degree. So then you expand the 2, get a 5, 6, 7. It's the second level set. And then from 5, 6, 7, get another level set, right? And then you order in this order, then your matrix will look like something like this. You still, within the band, there are zeros, but pretty much for this particular picture, since each level you have only 3 vertices, so you can actually, the matrix here, you can put this in the form which is like a block tridiagonal form, okay? And so that's the SIAM Cartier-Mackey ordering. And then later somehow people found that reverse this order. So you go through this, you still do this level set breadth first expansion, and then after you find this order, you just reverse it. Instead of 1 to n, you say n to 1 to flip it. And somehow people find that this reverse RCM is better in terms of the quality. And there's not much theory about this. Okay, so this is useful for SPMV, right? Remember we talk about a distributed SPMV. If you can reduce the bandwidth, then you don't need to fetch X vector from many places. So that's good for SPMV. And it turns out it's also good for this envelope profile solver. So remember we saw this picture. So in the old days, the simple data structure they use is to use this profile, just to store all these row by row, store this column by column, and then just keep track of the first non-zero of each column, first non-zero of this each row. This kind of representation is simpler than CCS and CRS that we're dealing with. But it's less. It's a little more expensive in terms of memory and operation. But then suppose you are dealing with right now, even in industry, since their code come from many years ago. So in industry, the code, the structural engineering code, a lot of them they still use this storage. So for this kind of storage, you can pre-process to add this RCM ordering in order to reduce the bandwidth, so that you get a good locality there. So then this is one of the a property of this is the envelope of L plus U is actually the same as the envelope of A for Gaussian elimination. You can think about this afterwards as a homework. So the thing is the envelope, we can think about an envelope versus general solvers, right? So in the, here I give you one example. There are three orderings for this. One is natural ordering, and one is the using RCM, reduce the bandwidth, and then using the minimum degree ordering. So now I'm looking at the envelope size, which is the sum of all the bandwidth. So every row has a bandwidth, every row column has a bandwidth. I just take the sum of all of them. So that's the definition of envelope. And then you can see that so with natural ordering, you get the envelope is this. And after I run the RCM ordering, the envelope is reduced. So it's better this compare if you are using envelope solver. But for the minimum degree, of course, the envelope is much bigger, because minimum degree you have to keep track of all these big. The first non-zero is very small, so all these you have to be kept in your envelope. So for minimum degree, envelope is actually very big. So, but then if you don't use the envelope solver, use just the general solver, the number of non-zero is much smaller than the envelope solver. So this several picture I want to show you is really to show you that if you are using minimum degree, then it's not good to apply this for envelope solver, for envelope storage. But if you are using an envelope solver, then it's better to use RCM, not to use minimum degree. Okay. So there are a lot of things when you do a lot of different ordering algorithms, different solver storage, and how do you match them together? It's very complicated issue. Okay, so then for non-symmetric matrix, the situation becomes much more complicated. And essentially, we don't have very good tool to directly work on non-symmetric matrix, non-symmetric graph. Non-symmetric graph, usually we use directed graph, okay. But so what most people, very often we use is to borrow the technique from symmetric matrix, which means you have to symmetrize your matrix. And there are two ways to symmetrize it. One is you take A plus A transpose. The structure, right now we only talk about structure, not the values, okay. So one is you take A plus A transpose. Another way of doing this symmetrize the matrix is to take A transpose times A. And those are essentially two ways to symmetrize the matrix. And then you look at the graph of this symmetrized matrix to run your minimum degree or Nancy dissection, and then apply this ordering non-symmetrically to the matrix A. So then the question is for whether you want to do A plus A transpose or A transpose A, which graph do you want to use? And you can imagine that A plus A transpose graph is sparser, right? Because A transpose A, you have to multiply things together. There are a lot of field. So this graph is usually smaller, it's better. But this works only if you do diagonal pivoting. So for example, the solver, we developed SuperLU, the parallel distributed version, SuperLU library. We use the static pivoting, and during numerical factorization, we just pivot on the diagonal. And in this case, this graph model, A plus A transpose, is a good model. And the homework I put in the exercise at the end of this lecture is for you to show that if you have a Cholesky factor of A plus A transpose, okay, ignore the numerical value, just look at the Cholesky factor, the pattern. And then suppose you want to factor this A as a LU without pivoting. Then the structure, the non-zero structure of this LU factor is actually contained in the LU, the non-zero structure of this Cholesky factor, the two parts. So this is the one of the homework assignment you can do. This one is relatively simple. And the other one is suppose you do partial pivoting when you do the LU factorization, meaning that when I factor A equals to LU, then we do each time I pick up at each column, I pick up the biggest element from this column and swap into the current pivot. So there's a permutation matrix involved. Is it 8:45 now? Okay. So for partial pivoting, there's a permutation matrix involved. And then what's the property here shows is that suppose you look at a Cholesky factor of A transpose times A. And then for any permutation, when you do LU for A, then this Cholesky factor of A transpose A would contain all the structure of LU, regardless of your partial pivoting choice. So that's a very strong statement. That just says, suppose you know the Cholesky factor structure, then you can try to minimize this field for this Cholesky factor, and this will tend to minimize the field of the LU for any numerical pivoting you are going to do. So that's the scheme. A lot of partial pivoting code, we use this to try to minimize the field. That's another level of heuristic. I'm using certain upper bound to try to minimize the field of LU. So in fact, in reality, the bound could be very loose compared to what happened. So this property is another homework assignment which you will do. It's not too hard. Just look at the sparsity pattern of each column of A, and then do the A transpose A, what's the sparsity pattern looks like, then you'll figure out. It's not hard. Okay. So for the unsymmetric, I mentioned that we can generalize a little bit this quotient graph, the minimum degree. So the unsymmetric version actually was also discovered some time ago. It's called this person named Markowitz. And now I have a non-symmetric matrix. The first step I have two non-zeros in the first column, three non-zeros in the second column. Again, after eliminating the first equation variable, you get these 6 elements, 2 by 3. It's potentially all field, but some of them may already be non-zero. So then for non-symmetric here, the handy tool, the graph model we use is a bipartite graph. You cannot really use the undirected graph, and for directed graph, it's not so convenient for us to use. So we use this bipartite graph. We direct vertex 1 is connected to 3 of those, and then R1 is connected to so R1 is connected to only 1. R2 is connected only 1. So you have a row set of vertices, column set of vertices. And after removing the first vertex, all the remaining vertices will become fully connected. And this is not it's not correctly the clique in the computer science term, but we call this biclique. So it's all the vertices from row set will be directed to all the vertices of column sets. So it's still like the clique concept, and it's an upper bound. Okay, but this works only we do the diagonal pivoting. If we don't do numerical pivoting. So then we can extend this the symmetric quotient graph model to the bipartite quotient graph. And then we have the same asymptotic complexity as the symmetric minimum degree algorithm. So the space is bounded by this, is almost linear, and the time is bounded by this, n times m. So then we did the experiment with over 50 unsymmetric matrices compared with applying symmetric minimum degree on the A transpose plus A on this symmetrized graph. So the reduction in field, because here if you do directly non-symmetric matrix, so you take a better advantage. You are not making one-step approximation like here. Here you are approximating your elimination. So here we have better quality. Reduction in field on average is 88%. The best case could be more than 2 times the reduction. And then the reduction in the floating point operation average is 77%. The best case we get almost 100-fold reduction in the floating point operation. So, then there's so this is about for unsymmetric extension of minimum degree, and there's also some work, but it's not quite a lot, about using graph partitioning for unsymmetric LU. Nested dissection, for example, graph partitioning for LU. So there's something called a hypergraph partition. And it's similar to apply nested dissection to this symmetrized matrix, but using hypergraph, you don't need to compute A transpose A. So you can do an exercise even in MATLAB, for example, generate a sparse matrix and compute A transpose A. In fact, it can be a lot of non-zeros in A transpose A compared to original A. So if you can manage to do something without forming this, it's very good. So then the issue is now I have shown you a lot of issues in sparse GE. So then we can compare sparse GE versus dense GE. In dense GE, we're all familiar with pivoting, right? We have been talking about pivoting. So we have most commonly we use a partial pivoting, which means we only do the row permutation or column permutation. But as for some algorithm, linear algebra algorithm, if you want to have a more stable algorithm, it's necessary to do both row and column pivoting, and they call this a complete pivoting. And in some cases, but most commonly, we don't need to do complete pivoting. So that's the role of permutation in dense GE, is really to stabilize the algorithm, maintain stability, and then to control the element growth. But then in sparse GE, there are a lot of different criteria we're looking at. So we still have a row permutation, column permutation, right? But this permutation, the purpose of this is not only to maintain stability, but also to preserve sparsity, to try to reduce the number of fields. And also for parallel computing, we want to get a good ordering which increase the parallelism, basically reduce the number of dependent tasks among the elimination tree. So if you get an ordering which has a much wider bushy elimination tree, then you have more parallelism in there. And then also in the sparse case, if you do dynamic pivoting like a partial pivoting, then your data structure, the amount of field you generated is actually changing dynamically, so that you need to design very complicated data structure to on the fly to whenever you detect there's new field generated somehow malloc free. It can be expensive. So then people are using some alternative pivoting strategy like threshold pivoting. So threshold pivoting, just to say, suppose within this column, partial pivoting wants to pick up the largest element, but threshold pivoting could say pick up the element which is maybe 10 times within a factor of 10 of largest, not necessarily the biggest. So that you have some freedom within each column to pick up some element. And this element connectivity to the neighbors maybe is small, so that gives you better sparsity. So that's the trade-off between stability and sparsity. So there are a lot of criteria trade-off people will think about for sparse factorization. So I just want to mention a little bit the issue of pivoting in the sparse case. So numerical pivoting can be very bad for performance of sparse factorization. For example, I give you little matrix part here. Suppose right now your GE is at this step, right? And then you got a pivot element, diagonal element is small, but then one of the biggest element B is here. So in partial pivoting, you would want to swap these two rows before you do GE, okay? But then you can see in sparse case what would happen. What's the impact to this row? Suppose either you use this row as pivot or use that row as pivot. So from sparsity point of view, which pivot is better? S is better because you will generate only 2 non-zeros. But from numerical point of view, you want to use B because you got more stable. But on the other hand, if you use B as a pivot, you will get 3 non-zeros. Okay. So that's the thing I was mentioning. People have to balance a little bit whether you want most stable, like partial pivoting more strict, or you want to relax a little bit, give some freedom to maintain sparsity. So in the distributed, and also this partial pivoting is, when you do this swapping, it's very difficult to implement in a bigger machine. So in distributed solver, for example, the solver we have worked on, where did it go? Okay, here. So we have worked on is we are actually using this something called a static pivoting. So before factorization, we first do the scaling 2 diagonal matrices. We scale the matrix so that their magnitude are roughly the same. And then we find a permutation to permute A to maximize the diagonal of this equilibrated matrix. So our permutation, and we still have a row permutation, but it's obtained based on the value of A, not based on the dynamic L and U. And the algorithm to find this is something called a bipartite graph. Look at a non-symmetric matrix bipartite graph and run the maximum weighted matching algorithm to pick up the n edges, which has the maximum element, and then swap the rows to put the edges to the diagonal. So that's a very popular, standard computer science algorithm, maximum weighted bipartite matching algorithm. And once you did this pre-processing step, during the factorization, we use this A prime matrix to do the factorization. Then we don't do any permutation anymore, so that we can set up the data structure very nicely without too much communication. And it's, of course, this static pivoting numerically is slightly less stable than partial pivoting. So we can apply a few steps of iterative refinement in the end to stabilize the algorithm. So in practice, this code has been very stable, has been used by a lot of people. So let's take a 10 minutes break when we come back. So I think we'll start from in this room to at least to go through the presentation, and maybe for the rest of the session we'll be here, or depends on how you feel and Peter, the assistants, they feel. So this afternoon will be entirely, after presentation will be entirely Peter's session, the homework. Okay, so that's afternoon plan. And then over the break, there is a question about iterative refinement. So you all know iterative refinement, right? Or it's familiar? So what it does is it's cheaper than a real iterative solver. So suppose you have let's say you have a not so great LU factorization or somewhat approximate factorization. Then you compute your first solution, and then you compute the first residual. And maybe in the beginning it's a little large. So then you repeat this correction to correct your solution. So you solve a little correction term using your residual, and then add this into your solution, which becomes more accurate. And then to prepare for the next iteration, compute another residual to run through this. That's the iterative refinement process. So for these 3 statements, is it expensive? After I already have the LU? No. So this solve is trivial. I mean, not trivial, it's the triangular solve, right? And that's just a 1 vector addition, and that's the matrix vector multiplication. So it's a relatively cheap iteration, and then for most of the problems we have seen using static pivoting, we only need 2 or 3 steps. That's good enough to get a very accurate X. Okay. So let's see. So that's why this the relaxed pivoting, static pivoting, or the threshold pivoting is used very commonly in all the software, the sparse matrix software, and just using this a little bit post-processing step. refinement, which give you very good solution. And then you can avoid a lot of expensive problem during factorization. So I'll just want to summarize this lecture about several points that we have studied. And in this sparse factorization, this field, it's a big headache. But in order to find the best ordering for general graph. Remember I talked about ND, nested dissection, which I said it's optimal, but that's only for that's a special class of graph. For general graph, you cannot prove optimality. So for general graph, to find the optimal field reducing ordering is NP complete problem, meaning that you don't have a polynomial algorithm to get this. And then people develop a heuristic. We use a local approach, local greedy approach, minimum degree, and then global approach, nested dissection, which is optimal in special case. And then nowadays, basically for these two classes of algorithms, we know people have observed that this local minimum degree is good for medium-sized problem, not for very big, because it doesn't have a global picture. Whereas the nested dissection graph partitioning starts top down. You look at the global graph, find the separator, continue going down. So global scheme, nested dissection, it works very well for very large problem, for extremely large problem. So what people have used is the combination of the two. So basically you use a global nested dissection, stop at certain level. Once your matrix, each piece becomes small enough, then you will apply this local minimum degree ordering. So that's a very natural thing to do. And then there's also numerical pivoting. The people use some heuristic to trade off stability with sparsity and parallelism. So partial pivoting is replaced by threshold pivoting or static pivoting. Okay, so those are the permutation issue. So then in the sparse GE, if you look at the whole solution process, there are several stages. All the issues could be touched by, at each stage. The first stage is a combinatorial problem. You find the ordering to minimize the field and maximize parallelism. So that's the first pre-processing stage. And the second pre-processing stage is to predict the filling position. So once you fix the ordering, and suppose you don't do any numerical permutation, then the number of non-zeros, so you should be able to find using your graph algorithm, like graph traversal, finding the transitive closure, those kind of algorithm, you can find out all the filling positions. Then you can set up your CCS or CRS storage scheme. Because if you don't know where the non-zero position is, you cannot set up the data structure. So this step is called symbolic factorization. And then you design the efficient data structure. It depends on which algorithm you use, what kind of storage scheme, whether row-oriented, column-oriented, or block-wise, which we'll see later. We have block version. So then you use set up compressed storage scheme. And after all these pre-processing steps, in the end, you get to numerical factorization. That's your matrix computation. So it's a lot of things going on. And for the sparse Cholesky QR, because the pivot order could be determined, then so all these steps can be separate. But suppose you do sparse LU with pivoting, with dynamic pivoting, then step 2 and 4, they have to be interleaved in the algorithm, because every time you did the pivoting, it will change the trading matrix non-zero pattern. Then you have to change your data structure, symbolic factorization. So that's the general algorithm. And then the references, so I'll just point out, there are 3 books for talking about sparse direct method. Let's see. Yeah, so these are the first 3 books. And this book is very good for all these talking about reachable set. And of course, Alan George invented the nested dissection. So that's a classical book. And this is a relatively recent book published by SIAM. It's a Tim Davis book. And he uses his code, C-sparse code, as a base toolbox to go through all the chapters. Exercise is based on you can do all the problems, all the algorithms could use his code to. It's like in MATLAB, you can play with it. So that's very good for hands-on if you want to learn this. And then for graph partitioning, I mentioned that this is a PT Sculpt package and Parmetes package. These two references, they are available, can be downloaded. And there's a more recent, more powerful Zoltan, this parallel partitioning load balancing software, which is developed by one of the Sandia lab. It's also another US Department of Energy research lab. It's similar like ours. So Joseph Liu, this paper is a very good overall survey, and that touched all the details about different aspects about minimum degree algorithm. And then so our paper here is about the non-symmetric extension to minimum degree. So that's the reference. Okay, so what are the exercises? I mentioned I'd like you to, so there's one PDF file in this in this folder, hands-on exercise folder. There are several simple graphs. I want you to go through them to think about what's the best elimination order to get a minimum field. And then these two problems you can think about. The structure containment property of these two. That's useful for non-symmetric LU factorization, so you can prove. It's not difficult. Oh. So let's see. So that's, we finished the combinatorial aspect of Sparse GE. So now we can go to the actual numerical factorization. Are there any questions? Okay. So this lecture is mainly about the different way of doing the Gaussian elimination. And this actually, a lot of this is the different organization, data flow organization, left looking, right looking, also applies to dense matrix. So it's not just sparse. And then we'll talk about for high performance issue, then we don't do one column at a time. We try to find something called a supernode, which is dense submatrix, so that your numerical kernel is not only the level 1 blast, like SAXP kind of operation, but you can increase the level of blast by using supernode to call GEMM, so then you can get much better performance. Then we'll talk about sparse triangular solution. Okay, so let's start with dense Cholesky. And for dense Cholesky or dense LU, Cholesky is just half of, you do the symmetric factorization, you can save half of the storage, half of the operation. So there's also something called left looking and right looking. So left looking just means, so right now I'm doing the Cholesky factorization, and I have half of the matrix, the other half I don't need to do because it's always symmetric. So I don't need to work on any of these pieces. And it's a dense matrix, so the lower part is entirely dense. Left looking just means right now I'm working on the kth column of kth column, and everything on the left is already eliminated, finished. So I can use all the finished stuff, like update my destination column here. And the right looking is different. Right looking is currently I'm at column K, right? But everything here is finished, and all the rest I'm trying to get all the rest to do the update the trailing matrix. So every time I have to look to my right to update the trailing matrix, whereas the left looking at this point, I only look at my left. I don't need to look at my right. So that's two different ways. And that's the pseudocode basically for symmetric is a little bit harder to think because you don't have the other part of the matrix. So what happens is, suppose you are at the kth column here. So this is your kth column. And then everything here is finished. So you want to accumulate all the update to your kth column. And remember that it's a symmetric matrix. So this part I computed, right? That means symmetrically I already have this part. This part is the same as this. So mathematically, I have this part, except I don't store this. I can fetch this part from here. Okay, so that's what this code does is. So the outer loop here is from 1 to n columns. And at the kth column, I go to each of the I row from k to n, from k to n, and then j column from 1 to k minus 1. So for each I row, I need to update my matrix, this vector column here. So this aik, the whole column will be updated by lij, which is lij, one of these elements, times lkj. Kj is just so one of these guys needs to multiply with this and then accumulate. So for each of the column here, I need to do a dot product with this, add into here, update here. So each row here, I do a dot product with this, update here. So that's the left-looking algorithm. And the right-looking is different. So right-looking is at each column, I will do the scaling here. I'll do the diagonal, take the square root, and then I do the scaling of the column. Then I need to take the whole column and symmetrically the whole row to update into here. Okay, so the right-looking is so this column is finished. So then I use this column symmetrically mirror here. I have this column, this row, right? So these are the same. I computed this part, and this part could be used as this piece. And then I take the outer product to update into here. But of course, you only do half of, so for this guy, you don't need to do it. Only do half of it. Okay, so that's a dense Cholesky. And similarly for sparse Cholesky, you can do the same thing. So here we use a simple example to illustrate the process. So our reference case is a regular 3x3 grid. It's simple, and right now I'm numbering this like a nested dissection kind. So 1, 2, 3, and then 4, 5, 6, 7, 8, 9 separator at the top here. And then I use the notation. C div is divide the column by a scalar, which is the scaling the column, and C mod of j and k, meaning that I modified column k using update column j using column k. Okay, so this is my destination column, and then I use this notation L of 1 to k, the jth column of L from row 1 to k, and the structure of that. So this is just the structure, the non-zero position. This notation doesn't care about the numerical values, just the pattern. So that the sparse left-looking Cholesky is at this step, I have everything on the left is finished. So look at this picture here. And then I need to update the current column. So basically, I need to take the dot product of this column with all of those. So what it does is that from column j to n outside is for each of the k in the structure of the jth row, in the structure of jth row, all these non-zero index k, then I will do a column update from kth column updated into the jth column. And then after that, I do a column scaling. Okay. And then you look at the elimination tree of this little matrix, you can see that it's left looking, it's actually fetching the data from the descendants of the tree. So for example, this 7th column, it needs data from column 3 and column 1 and column 6 and 4. So this is given, so column j is updated with all the columns that have a non-zero on row j. So all the columns k which has a non-zero in row k, then it will update this column j, right? So the indices here is 1, 3, 4, 6. 1, 3, 4, 6. These 4 columns will update the jth column. So this corresponds to we always use this tree to help us with the computation. So this corresponds to receiving updates from nodes, which is lower in the subtree rooted at J. And the field graph is needs to determine the structure of each row. So that's left looking. And the right looking is corresponding to this picture. So for each column, right now I'm at this column, I need to accumulate the update here. So for each column here, I first do the column scaling, and then I look at all the indices which are already in this column. So after variable k is eliminated, then column k is used to update all the columns corresponding to the non-zeros in column k. So that means here, the column k non-zero is 7, 8, 9, right? So then all the columns, the later columns 7, 8, 9 will be updated. It's because of this outer product relation. And then look at the tree here. The data flow is different. So right now we are at column 3. Then I need this column 3 need to be used to update the ancestors 7, 8, and 9. They are all the ancestors. So the left looking is I go back down the tree, look at some of the descendants. I need to accumulate the update. And the right looking is I look up the tree. My current column needs to update some of the ancestors. Okay, so for LU, it's similar. And now it's actually, LU is slightly easier to understand because you have both the data structure here. For symmetric factorization, you have to think about it in the mirror. But here, you just have everything here. So for the left looking, what you do is look at the non-zero pattern of this column. And all the non-zeros in this U, the column here, the U column here, the Jth column, the upper part, all the non-zero k index tells you which column before this will update this Jth column. So the k before that will update this. And then after that, you do the column scaling here. So the left looking here is active part is the column, and everything here is done. Everything on your right is not touched in the factorization. And the right looking, what you do is, currently you are at this column, right? And then you first do the column scaling, and then you look at the row of this U and the column of this L. Then you look at the non-zero pad structure. Again, just pick up the indices J, which is in the row here, and then do the update. So the active part is the trading matrix here. Okay, so then that's the simple algorithm description. But for high performance, then you actually have to do a lot more than this simple in order to get a very fast speed. The first thing we need to do is to do the blocking in order to increase what we call the arithmetic intensity, right? And another thing for parallel machine we need to do is try to aggregate small messages into one larger message. Remember we look at some real data about latency and bandwidth. So latency is very expensive. It's a lot of cycles. Each message, it could be the latency you have to pay. It's equivalent to over 10,000 floating point operations. So if you can try to reduce the number of messages, which will reduce the cost due to latency, that's very important. And this is already, these techniques are already done in LAPACK, ScalarPack, and essentially we need to adopt all these in sparse factorization in the modern, new generation of sparse software. So blocking, we call this supernode in the sparse factorization. So you use, then the data storage you use is not the scalar version, not the column-wise or row-wise CRS or CCS, but we use a blocked version of those. So the picture here is, that's your L and U factor, right? So you look at the field pattern of L and U, then you can find out that some of the adjacent columns, they might have the same row structure here. So you have several columns here, and the diagonal is fully dense, for example, and the off-diagonal, their row structure the same. Then you can imagine that you can represent this off-diagonal block, diagonal block, off-diagonal block as a dense block. Store them only in the storage. So what you do in the storage is this is your diagonal block, and then this is your one off-diagonal block. So this is stored as a dense matrix block, okay? And those part, this is 0 part you don't store. You just squeeze them together. That's how you store them. And then you can, with this storage, you can call the GEMM routine, okay? So that's from matrix point of view, it's called a supernode. And from a graph point of view, look at the portion of the graph corresponding to this matrix. The graph is actually 6, 7, 8, 9, these 4 vertices, 4 columns corresponding to the 4 vertices. They are actually fully connected, right? Because of this dense structure, each one is connected to each other. So then you can build a graph which is consists of all these super vertices, super nodes, instead of the graph, each vertex, each column is 1 vertex. That's the original graph. But with this analysis, once you identify the super node, you can have a much smaller graph. Then in a smaller graph, each vertex corresponding to these several columns. And then when you do the symbolic factorization, graph traversal, and all this depth first search, breadth first search will be much cheaper since you are dealing with a much smaller graph. So collapse these 4 nodes into 1 node. Okay, so that's where with this super node you can save both numerically, you can do high-level blast operation, and for symbolically you can use a coarser, smaller graph to deal with the pre-processing step. So non-symmetric supernode. So this is my original matrix A, and this is after GE, the factor LU with some fill. And then you can identify the supernode structure. The first 2 columns, they have the same structure. The 3rd column is different from every other. So the 3rd column is a singleton, it's 1 supernode. And then the next 3 columns are supernode. The last 4 is a supernode. And what's the advantage of doing this? So this actually was the data collected when I was in my thesis a long time ago, but it's still valid even for current machine. So what we did here is we look at 22 matrices, different sparse matrices. And then this is the speed up of blocked version, the supernode version versus the column-wise version. So this is not parallel, has nothing to do with parallel. It's just that we use a new data structure to represent the supernode, and then call blast 3 routine. And then these matrices are sorted in increasing order of reuse ratio, which is the number of flops divided by number of non-zeros. It's the similar measure as our arithmetic intensity, right? So you see that with bigger and bigger arithmetic intensity, then the speed up is getting bigger. So even for sequential machine, without parallelism, just using this supernode organization, you can get over 10 times the speed up compared with just a column-wise algorithm. Okay. And so that's the supernode. And then there's something called a multifrontal factorization, which is very similar to, idea is very similar like a supernode. But it's organized the factorization in a different way, and it's natural to get the supernode in this way. So we still start with our little 3x3 matrix, and then the elimination tree is given by this, in this order. That's the original matrix. The multifrontal factorization is for each node of this tree from leaves to root. So we always do the elimination from bottom to top, leaves to root. We sum the own row column of A with the children's update matrices into the frontal matrix. And then we eliminate the current variable from frontal matrix to get the update matrix, then pass the update matrix to parent. So what this means is that look at the first step. So the first step, we do the first step, we have 3 non-zeros, 1, 3, 7, right? 1, 3, 7. So you get, after you eliminate the variable 1, you will get the update. This 2 by 2 matrix needs to be passed to the parents, to the Schur complement, update to the Schur complement. So this is our F1, the first frontal matrix. And then it generates update matrix 1, 3, 3, 7, okay, dense matrix. And then for the second vertex here, similarly, you get when you eliminate 2, then you get 3, 9 connected. So 3, 9 will be connected. Here, the frontal matrix at node 2 is this matrix, and then the update matrix is given by this another 2 by 2 matrix. So these 2 update matrices, right now it's just the local on each corresponding to this node, corresponding to that node. But this needs to be accumulated to the global trading Schur complement. So then the next step we do is to merge this update U1 matrix pass to the parent, and U2 matrix pass to the parent. In this case, the parent is 3, right? So at node 3, we have to get the U1 matrix coming from 3, 7. U1 is 3, 7. Okay, this piece, and then U2 is 3, 9. So U2 is 3, 9. This piece. So this piece needs to be merged together, to add together into the frontal matrix of node 3. And then we start eliminating node 3, get the another update matrix U3, which is 7, 8, 9. Because after you eliminate U3, it's going to be 7, 8, 9, they will be connected. And this U3 will be passed to U3's parent, which is 7. So this multifrontal is very similar, like right-looking, but it doesn't go to the ancestors of the tree. It only passes this update matrix to the parent. So there are a lot of temporary, this storage, U1, U2 is a temporary intermediate storage. They accumulate them gradually, go to the parent, and from the parent absorb into the parent frontal matrix. After elimination, they will go to push to the grandparent, to another, the parent of the parent. So it's just keep going like this. It's kind of it's a right-looking kind of algorithm, but it doesn't go to directly go to the ancestor. It's going through this path from parent to parent, parent, parent. In the end, pass through the ancestors. Okay. So that's at the end, that's your factor with all the field. So to summarize this multifrontal factorization, it's a variant of right-looking algorithm, but it really uses a supernode, as I mentioned. Each of these frontal matrix corresponding to the supernode we mentioned, not just one node. And all the arithmetic happens on the dense square submatrices, but the disadvantage of this algorithm is it needs extra memory to accumulate all the update matrices. So potentially this multifrontal code will needs more memory than right-looking or left-looking code. But on the other hand, it's easier to manage parallelism between, because all the parallelism you can imagine, all these subtree, independent subtree you can do in parallel, say give to 2 processors. But the 2 processors, they need to cooperate at this level, okay. So let's take a look at the triangular solution. So triangular solution in the dense case is relatively easy, but then in sparse case there are different ways. Again, it's based on this elimination tree, how you organize it, whether it's a row-oriented storage or column-oriented storage. Then you have for the tree, whether you need to go down to look at the parent, the descendants, or you need to go up to look at the ancestors. So this picture, this pseudocode is the dot product version, which is using the row-oriented compressed row storage, for example. And it's left-looking. So for example, it's at this stage, This is your x vector, that's your b vector at right-hand side. So everything here, all the components here, x is already computed. And then my next current step is compute this x of I, the ith component. So which means I need to accumulate the dot product of this row of the matrix with the corresponding x vectors, and then to update into the b. Then I do the division. So the first step here is I copy this b into x component, and then I use this the row of L to multiply with this j, and then to do the update, and in the end to do the division. Okay, so this is a dot product version, and then you can imagine that to get these non-zeros, they are actually just all the descendants. I need to get 1, 3, 4, 6. Those x components to multiply with those together in here, right? And then the back substitution is going backward from bottom to up here. So then you can reverse the, symmetrically, you can think about the column-oriented. Column-oriented, suppose your matrix is stored, your L matrix is stored in this way, and then you have to use the Saxby version in the internal calculation. So that means every time I will get I need to do the update to several of the x component. And only after all this done, in the end, I do the division like this. So that means, for example, for this picture, in order to get every time at the current column 3, after I computed x3 here, then I need to take the x3, scalar multiply the whole column, add it into the rest of the right-hand side, update the right-hand side. So that means I'm actually need to use my current solution to update all the ancestors along the tree. So it's a different data flow. And then one interesting thing about this is, suppose you have a right-hand side is sparse. So very often we solve the linear system, right-hand side is dense, but in some situation you need to solve the system, right-hand side is sparse. And in that case, you can save some work by being a little bit more clever. Instead of treating the whole vector, the whole vector maybe just have one non-zero. You don't want to do all the operations. And the graph model here we are looking at is the directed acyclic graph of this L matrix, the lower triangular. It's actually the lower triangular matrix of A, and which is defined as the edges is directed from high number from this two, from this high number to the low numbers. So it's actually this graph you can think about as from edges is directed from 3 to 1, and then this is 1, 2, 3, 4, 5, 6, 6 to 3. So you have 3 to, sorry, 3, sorry, this is 4. 4 to 1, and then 6 to 3, 6 to 3. So those are the definition of all the edges. It's look at the lower triangular matrix, and then to all the edges are defined, directed from high number to the low number. So that's a little picture of a small example. I have the right-hand side here. I have only 2 non-zeros, right? So then I don't need to worry about the first zero. So I don't need to do any operation with this. I only need to start from 2 and 3, since I only have these 2 non-zeros. Then the field, again, you can use the field theory, the field path theorem, which says that the number of non-zeros generated in X will be given by all the vertices which is reachable by going from 2, starting from 2 and 3, reaching to 4 in this case. There's only one new non-zero generated. So therefore, for the sparse triangular solve with the sparse right-hand side, you also have the 2 stages. One is a symbolic factorization, which starting with the non-zero position here, and then do the depth search of the graph, find all the non-zeros, the end point, end vertices, of the graph, which gives you the new non-zero field in the x vector. And then second stage is to do the numerical computation. So for the sparse right-hand side, you can do something clever like this, and you don't need to do all the calculation with the zeros. And your solution vector, in general, is still sparse. And the time complexity of this algorithm will be proportional to the number of flops. So you won't do more than the number of flops. So then, why is sparse triangular solution useful? In fact, if we think about the right-looking sparse LU algorithm, this just I showed a few slides back. When you do left-looking sparse LU, everything here is finished, and right now you're actively doing the update to this column, right? So you have some non-zeros here. And the operation here is really what we need to do is to use this L piece to do the triangular solve using the column of A, original non-zeros here, and then to get the piece which is in the U vector here. So this one is, this column is actually sparse right-hand side. And for this operation is a sparse triangular solve with a sparse right-hand side. So that's where this sparse triangular solve could be even useful in the sparse factorization. But in general, there are quite some applications you would have right-hand side which is sparse, not entirely dense. Okay, so that's about this lecture, the data organization, data flow, left-looking, right-looking, how do we incorporate a supernode, and another right-looking version, it's multifrontal organization. So let me say the references here. So this review paper, SIAM review paper, more than 20 years ago, but it's a very good summary of different organization, how the left-looking, right-looking multifrontal works. So it's a very good survey paper. And then Ed Rothberg, in his thesis, during his thesis work, he has done a lot of sparse Cholesky factorization with a different variation, different kind of blocking on his modern machine at his time. So that was about 20 years ago when he was doing the thesis. But those papers are still very good to read, to understand this kind of a high performance issue underneath that. So my thesis, I did the sparse LU, supernodal version of sparse LU, which was more than 10 years ago. So in this SIMAX paper, that's about left-looking LU and how do you do pivoting. So this code actually has partial pivoting. It's complicated. And that's this actually is the basis of our software, SuperLU, which is available right now on the website. And then the multifrontal method was actually invented by Ian Duff and John Reed. But their paper, they invented that 86 paper was the first paper. They mentioned this algorithm. But that paper is not so easy to understand, to follow. And Joseph Liu wrote this paper, review paper, was very good to summarize from a mathematical point of view, from matrix point of view, how this multifrontal method work for sparse solution, sparse solver. Okay. So actually, there's not much exercise for you. You have enough exercise, by the way. That's good for you. So what you can do is really, this is a dense code in the hands-on exercise. The code is fully there. So what you can do is to run the code. It's an OpenMP code, but it's a dense LU. It's more involved with the partial pivoting. So it's more involved than dense GEMM you are working on. And it's an OpenMP code, so you can study that. Okay, so that's this lecture. I think we have a few minutes we can get started a little bit. Are there any questions? So let's see, let me just, because today is, you have a long weekend, so we'll just see what's the plan here. Okay. Okay, so let's just capture what's the plan. Where are we now? So we finished all these 4 lectures, and then we'll spend maybe an hour or so, or maybe a little more, on this parallelization for factorization. We talked about parallelization for GEMM, and factorization is, first of all, it's a sparse, and then parallel is much more evolved. So we'll spend about 1 hour or so. And then we'll talk about 2 approximate factorization as a preconditioning technique, then later in the end to the hybrid method. Okay, so that's where we are. Okay, so parallel. So there are a lot of code developed over the years on shared memory machine, distributed memory machine, and I will mostly talk about. Mention the algorithm of different type of algorithm, but for the detailed performance analysis, detailed how the algorithm work, I'll mostly use the software that we developed, SuperLU. We have a sequential, we have shared memory, SuperLU MT, and also SuperLU distributed. So I will mostly use the algorithm there to illustrate all the details. Okay, so let's see. So for the shared memory machine, it's relatively easy. You have the algorithm is left looking, so we just do the whole matrix is available. Every process could see this matrix, okay? So every process will say, this picture say 2 processes. We'll take one panel of the matrix, and a second process will take another panel of the matrix, do the factorization. And it's a left looking scheme, so that this process only needs to say, take all the part of the matrix finished here, and then accumulate update here. Then process 2 will say, take all the finished piece here, do the update on this panel. So right now, each stripe is actually 2 vertices, so I'm doing like 2 columns at a time in order to get to use, for example, to better cache utilization. But in general, this can be bigger, so usually we take like 20 panels at a time. So the question is, just look at this update. You can have for the piece of update from here to here, and also for the piece of the update from this part to this light pink, they are independent, right? So what it means that all the subtree, the matrix corresponding to those subtree, can be updated simultaneously to here and simultaneously to here. They are not dependent. You don't have concurrent write. But then look at the matrix here. I have to accumulate some of the update from my neighbor, P1 process, right? If this guy is not finished, then I cannot go ahead to do the next part, because I have to wait for the update from here. From the tree, elimination tree point of view, is P2 has to wait for that piece to finish in order to accumulate this update to here. Since P2 needs update from all of these part. So if that one, P1 is not finished, I have to wait. And that's where there's some synchronization going on you need to manage. And apart from this, shared memory code is relatively easy to manage. There's no concept of distribution. All the tree, all the matrix is in global shared memory. And then you need to make sure coordinate, when this part is not finished, then you need to wait a little bit. So because of this synchronization, this dependency, you actually cannot get a perfect speed up. And when I was, that was about over 10 years ago, at that time, the shared memory machine, I could get about a 12 or, at most, I said over, but it's about a 12-fold speed up on 16 CPUs. You can never get like a 16-fold speedup. So that's a shared memory algorithm, and then we can, next time we can take a look at some. The code is still very good. We can take next time we'll take a look at the performance on new machines. Okay, so we'll stop here.